There is a number. It has no name a stranger would recognize. It has no mass, no color, no place you could point to in the night sky. Physicists call it W. And the value of that one number, whether it sits at -1 or a hair above or a hair below, decides whether everything you have ever seen ends frozen and silent, or is torn apart down to the last atom. Right now, we cannot measure it precisely enough to know which. What we can measure is this. The universe is expanding faster than it should. Two teams, using two different methods, set out to measure how fast. One read the light of the infant cosmos, the other read the dying flares of distant stars. They expected the same answer. They got 2. The gap between them has held for more than a decade, through every recheck, and it has not closed. Then, in 2025, a third instrument looked at 14 million galaxies and reported that the number deciding our fate may not be fixed at all. It may be moving. Every model built to explain that has failed to account for what the data show. One number stands between a slow, cold death and a final, violent unmaking, and we cannot yet read which way it points. The first people to notice that something was wrong were not looking for the end of the universe. They were trying to do something that sounds almost boring by comparison. They were trying to measure how fast the universe is growing. That number has a name, the Hubble constant. It tells you how quickly the space between galaxies is stretching. The further away a galaxy sits, the faster it recedes, and the Hubble constant is the rate of that retreat. You measure it in a strange-looking unit, kilometers per second per megaparsec. A megaparsec is 3.26 million light-years, about 19 quintillion kilometers, roughly 12 quintillion miles. So when we say the universe is expanding at 67 kilometers per second per megaparsec, we mean that a galaxy sitting 3.26 million light-years away is drifting away from us at 67 kilometers, about 42 miles every second. A galaxy twice as far drifts twice as fast. There are two ways to measure that rate, and this is where the trouble begins. The first way looks backward to the beginning. When the universe was 380,000 years old, it cooled enough for light to travel freely for the first time. That first light is still arriving today, stretched by billions of years of expansion into a faint microwave glow that fills the entire sky. We call it the cosmic microwave background. It is the oldest thing anyone has ever seen. From 2009 to 2013, a European spacecraft named Planck mapped that glow with extraordinary precision. Feed that map into the standard model of cosmology, and it hands you the expansion rate of the early universe. The number it returns is 67.4 kilometers per second per megaparsec, give or take half a unit. The second way looks at the universe nearby, here and now. A team led by the astronomer Adam Riess, working with the Hubble Space Telescope, builds what is called a distance ladder. They use pulsing stars called Cepheid variables, whose brightness tells you how far away they are. Then they use exploding stars, Type 1a supernovae, each one detonating with nearly the same intrinsic brightness, like a standard candle you can see across billions of light years. Rung by rung, they measure out into the cosmos and read the expansion rate of the modern universe directly. Their number is 73.04, give or take about 1. 67.4, 73.04. Those two numbers are supposed to be the same number. They are the same quantity, the same universe, measured two different ways. They do not agree. The gap is about 9%, and it has not gone away. When a disagreement like this first appears, every scientist assumes someone made a mistake. That is the correct first assumption. So both teams went back and rechecked. They re-examined their instruments, their calibrations, their assumptions, their statistics. They did it for years. The error bars on both measurements shrank. And as they shrank, the gap between them did not. It sharpened. Consider what that means. Picture two surveyors hired to measure the same river. One measures from the source in the mountains, the other measures from the mouth at the sea. They use different equipment, different teams, different methods. When they finish, their numbers should agree, because it is one river. Suppose they differ. You would assume one of them made an error, and you would send them back to check. Now suppose they both check 3 separate times, and each time their own measurement gets more precise and more confident, and the two of them still disagree. At some point, you stop questioning the instruments. You start wondering whether the river is doing something neither of them expected. This disagreement now has a name: the Hubble tension. By the standards physicists use, the gap has grown to more than 5 sigma. 5 sigma is the threshold at which a result stops being a curiosity and becomes a discovery. In plain terms, the odds that this disagreement is a random statistical fluke are less than 1 in 3.5 million. Something real is producing it. And after more than a decade, no one can say with confidence what. What does it mean that the 2 best measurements we have of the same universe refuse to agree, and refuse to be reconciled? Hold that question. To understand why a 9% disagreement is so threatening, you have to understand what is driving the expansion in the first place. And the honest answer is that we named it before we understood it, and we still do not understand it. For most of the 20th century, the assumption was simple. The universe is full of matter. Matter pulls on matter through gravity, and gravity is attractive. So the expansion that began at the Big Bang should be slowing down. Galaxies should be putting on the brakes. The only real question was whether they would slow to a stop, or even reverse, and fall back together. In the late 1990s, 2 independent teams set out to measure that deceleration. One was the supernova cosmology project, led by Saul Perlmutter at the Lawrence Berkeley Laboratory in California. The other was the High Z supernova search team, which included Schmidt and Adam Riess. Both teams used distant Type 1a supernovae to measure how the expansion had changed over billions of years. Both teams expected to measure how fast the universe was slowing down. In 1998, they found the opposite. The expansion is not slowing, it is speeding up. The distant supernovae were fainter than they should have been, which meant they were further away than a decelerating universe would put them. Something was pushing the universe apart, and that push was winning against all the gravity of all the matter in existence. The journal Science named it the breakthrough of the year. 13 years later, in 2011, Perlmutter, Schmidt, and Riess shared the Nobel Prize in Physics for the discovery. But a discovery and an explanation are not the same thing. They had found the effect. They had no idea what was causing it. So they gave the cause a placeholder name, a name that is really an admission of ignorance dressed in elegant language. They called it dark energy. There is an irony buried in that name, and it reaches back to the very beginning of modern cosmology. When Albert Einstein wrote down his equations of gravity in 1917, they refused to describe a static, unchanging universe. So he inserted an extra term by hand, a cosmological constant, a built-in tension woven into space itself, just strong enough to hold the cosmos still. A few years later, the physicists Alexander Friedmann and Georges Lemaitre derived solutions showing the universe need not be static at all. It could expand. And in 1929, Edwin Hubble proved it does. The galaxies are flying apart. Einstein, the story goes, abandoned his extra term and called it his greatest blunder. For 70 years it sat discarded in the history books. Then, in 1998, the supernova results brought it roaring back from the dead, because the simplest way to describe a universe accelerating apart was the exact term Einstein had thrown away. Saul Perlmutter, who shared the Nobel for the discovery, put the reversal with dry understatement. Perhaps there was more insight in Einstein's blunder, he said, than in the best efforts of ordinary mortals. Here is what we actually know about dark energy. It makes up about 68% of everything in the universe. 68% of the entire energy budget of all reality. Dark matter, itself invisible and unidentified, makes up about 27%. Everything else, every star, every planet, every atom in your body, every object that has ever been seen or touched or named, all of it together is the remaining 5%. We live in the 5%. The 68% that dominates the fate of everything is something we cannot see, cannot collect, and cannot explain. This is the part that stays with me. Not that the universe is large, that the thing which will decide its ending is the thing we understand least. What we can do is describe how dark energy behaves, and that description comes down to a single parameter, the one I named at the start, W. Here is the first piece of real mathematics in this case, and it is simpler than it looks. Every form of energy has a pressure and a density. The equation of state, W, is the ratio of the two. In symbols, W equals P over rho, pressure divided by energy density. That is the entire definition. It is a single number that captures the character of a substance, how its pressure relates to how tightly its energy is packed. For ordinary matter, W is near zero. For radiation, light itself, W is 1/3. But dark energy is strange. To push the universe apart instead of letting it fall together, dark energy must have W more negative than -1/3. It must have negative pressure, a tension, not a push. And the exact value of W, how far below -1/3 it sits, is the whole game. That number does not just describe dark energy, it determines the ending. There are 3 doors, and W decides which one we walk through. If W is exactly -1, dark energy is what we call a cosmological constant. Its density never changes. As space expands, you get more space, and every cubic meter of it holds the same faint amount of this energy. By one estimate, the energy equivalent of a single hydrogen atom spread across each cubic meter of the cosmos. This is the mainstream model. It has a name, lambda CDM, and it has been the standard picture for about 30 years. It leads to one ending. We will come to that ending, and it is colder than you think. If W is between -1 and -1/3, dark energy slowly thins out as the universe grows. The push weakens over time. Galaxies and galaxy clusters survive. This version has a name too, quintessence. And if W is less than -1, if it sits even slightly below that line, everything changes. This is the door no one wanted to find. Cross that line, and dark energy does something that no familiar substance in the universe does. As space expands, its density does not stay constant, and it does not thin out. It grows. The more the universe expands, the stronger the push becomes. And a push that strengthens without limit has only one destination. That third region, below -1, has a name. Physicists call it phantom energy. And that ending has a name that tells you everything: the Big Rip. The line itself, W equals exactly -1, has a name as well: the phantom divide. On one side, a slow ending, on the other, a violent one. And everything now depends on which side of that razor-thin line the real value of W actually lies. So you can see why the Hubble tension stopped being a footnote. For years, the assumption was that W sits at exactly -1, a clean cosmological constant, the cosmos winding down with mathematical elegance. But the moment our measurements stopped agreeing with each other, that assumption became something we could no longer take for granted. If the simple model were correct, the numbers would line up. They do not line up. And that opened a question most cosmologists had spent 2 decades keeping closed. Maybe W is not -1. Maybe it is not even constant. In March of 2025, that question stopped being abstract. There is an instrument at Kitt Peak in Arizona called DESI, the Dark Energy Spectroscopic Instrument. It sits on the Male 4-meter telescope, and it is a machine built for one purpose: to measure the positions of galaxies across cosmic time and reconstruct the entire expansion history of the universe. It can capture the light of 5,000 galaxies at once. By its second data release, it had measured 14 million of them, on its way toward a goal of 40 million. DESI maps the expansion using a ruler frozen into the universe itself. In the hot plasma of the early cosmos, sound waves rippled outward and then froze in place when the universe cooled, leaving a faint but fixed scale stamped into the distribution of galaxies. A standard ruler, the same known size everywhere. By measuring how big that ruler appears at different distances, DESI can read how fast the universe was expanding at each epoch, stretching back billions of years. In March 2025, DESI released its second-year results, and they did not match the simple picture. When the DESI team combined their galaxy map with the cosmic microwave background and with supernova data, the best fit was not a constant W of -1. It was a W that changes over time. And the preference for that evolving dark energy over the simple cosmological constant came in, depending on which supernova dataset they used, somewhere between 2.8 and 4.2 sigma. In the DESI collaboration's own words, the preference for a dynamical dark energy model over lambda CDM ranged from 2.8 to 4.2 sigma. And, they wrote, it is clear that lambda CDM is being challenged. Listen to the people who took the measurement. Nathalie Palonque-Delabrouille, a DESI spokesperson, put it carefully. We do see an indication, she said, that the simplest model might not be the one that describes the universe. Lloyd Knox, a cosmologist at UC Davis, was blunter about the stakes. If it's confirmed that we're actually seeing an evolution of dark energy, he said, this would be a profoundly important discovery. A profoundly important discovery. That is the language scientists use when the floor they have been standing on for 30 years begins to move. And there is one more detail in the DESI result that I have to give you honestly, because it is strange in a way that matters, and the easy version of this story leaves it out. The evolving W that DESI prefers does not sit below -1 today. Today, it sits slightly above -1, in the quintessence range. It is in the past, around a redshift of 1/2, that the data hint W may have dipped below the line, into phantom territory before climbing back. Which means dark energy, if DESI is right, appears to have crossed the phantom divide. It crossed the very line that a single, simple field is mathematically forbidden from crossing. Hold that because it will matter enormously later. For now, sit with the shape of what these witnesses have found. Two measurements of the expansion that will not agree. A dominant energy we cannot identify. A parameter, W, that decides between a frozen ending and a violent one, measured right at the edge of the line that separates them. And the first real hint that this parameter does not even hold still, that it may move, and may have already crossed into the one regime no simple physics is supposed to allow. What does it mean that the number deciding the fate of everything is sitting exactly on the knife's edge between two endings, and may be moving? That is the anomaly. Now we work the evidence. The first piece of evidence is the mechanism itself. The precise reason a number slightly below -1 is not a small adjustment, but a death sentence. It comes down to a second equation, one that controls how the density of dark energy changes as the universe grows. Write it in plain terms. The density of dark energy scales as the size of the universe raised to the power of -3 times the quantity 1 plus W. That sounds abstract, so watch what the arithmetic does. If W equals -1, then 1 plus W is 0, and anything raised to the power of 0 is 1. The density never changes. That is the cosmological constant, the same energy in every cubic meter forever. But if W is less than -1, then 1 plus W is a negative number, and -3 times a negative number is positive. The density now scales as the universe raised to a positive power. The bigger the universe gets, the higher the density climbs. Sit with how strange that is. Every other substance you have ever encountered thins out when you give it more room. Spread a gas through a larger box and it becomes more diffuse. Stretch matter across more space and its density falls. Phantom energy does the reverse. Expansion feeds it. The more space there is, the more concentrated its push becomes, which expands space faster, which feeds it further. It is a runaway. One science writer described it without flinching. A W below -1 means the amount of your substance increases faster than the volume does as the universe expands. This, the writer added, should unsettle you. It unsettled the three physicists who first followed the arithmetic to its end. In February 2003, three researchers, Robert Caldwell of Dartmouth, Mark Kamionkowski, then at Caltech, and Nevin Weinberg, then a graduate student, submitted a paper with a title that did not bother to soften the blow: Phantom Energy and Cosmic Doomsday. It was published that August in Physical Review Letters. In it, they worked out exactly what happens to a universe where W stays below -1. And they produced something almost no physics paper contains: a timetable for the end of everything. The mechanism is the runaway density we described. As phantom energy grows without bound, the repulsion it generates grows with it, and that repulsion comes for every bound structure in a fixed order. Largest and most loosely held first, smallest and most tightly held last. There is even an equation for how long before the end each structure comes apart, and it has a chilling property. It does not depend on the size of the universe or how much matter it contains. It depends only on W and on how tightly a given structure is bound. The looser the binding, the earlier it dies. Caldwell and his colleagues ran the numbers for one specific value: W equals -1.5, just past the divide. Here is the timetable they produced. Starting from a present-day universe, the end arrives about 22 billion years from now. That sounds comfortably far away. It is not the distance that matters, it is the final sequence. About 1 billion years before the end, the repulsion grows strong enough to tear apart galaxy clusters, the largest gravitationally bound structures in existence, assemblies of thousands of galaxies. They are unstitched first. Then, roughly 60 million years before the end, our own galaxy, the Milky Way, is pulled apart, its 200 billion stars scattered into the growing dark. About 3 months before the end, the solar system is unbound. The Earth and every planet released from the Sun set adrift. Roughly 30 minutes before the end, the Earth itself comes apart, the gravity holding the planet together overwhelmed by the expansion now happening inside it. And then, the final instant. About 10 to the -19 seconds before the end, 1/10 billionth of 1 billionth of a second, atoms themselves are torn apart. The electromagnetic force that binds electrons to nuclei finally beaten. In the time after that, smaller than we have words for, the nuclei dissociate, and then the nucleons inside them. The scale factor of the universe goes to infinity in a finite time. Not the end of things in space, the end of space's ability to hold anything together at all. Picture it as a demolition, but a demolition run in a precise descending order, each charge timed. Superclusters, then galaxies, then stars and planets, then matter, then the atom, then the nucleus. The same force, growing on a fixed schedule, taking apart structure after structure as it climbs past each binding energy in turn. Electromagnetic binding in an atom is a matter of 10 to 20 electron volts. Nuclear binding is around 1 million electron volts per particle. Phantom energy, in this scenario, eventually exceeds them all. What does it mean that the physics permits an ending this specific? Not a fade, but a sequenced unmaking with a stopwatch attached. That is one door. Before we test which door the evidence actually favors, we have to lay out the rest of the evidence trail, because the Big Rip scenario carries problems of its own, and honest investigation means stating them plainly. The first problem is that phantom energy, the thing that drives the Big Rip, may not be physically allowed. To make W go below -1 with an actual field, you need that field to have something called negative kinetic energy. In the language of physics, a wrong sign term in its equations. Such a field has a nickname that tells you how theorists feel about it: a ghost. And ghost fields come with a catastrophe attached. In 2003 and 2004, the physicists James Klein, Sang-Yong John, and Guy Moore examined what a phantom ghost field would do to the vacuum of space, and their conclusion was severe. Such a theory, they wrote, has no probabilistic interpretation. It is therefore unphysical and should be dismissed. The vacuum would be violently unstable, decaying catastrophically. In its rawest form, the field that produces a big rip appears to tear quantum mechanics apart before it ever gets the chance to tear space apart. Even the authors of the original Big Rip paper were uneasy about what they had written down. Phantom energy, noted, violates the dominant energy condition, and they called it a cherished notion, one that helps prohibit time machines and wormholes. Read that again. To get a big rip, you have to break a rule that physicists rely on to keep time machines and wormholes out of the universe. Caldwell himself, writing earlier, had put it plainly. If observations allow W below -1, then the dominant component of the cosmic energy density may be stranger than anything expected. This is the honest texture of the evidence. The Big Rip is not a comfortable theory that physicists are eager to believe. It is a scenario most of them would prefer to rule out, propped up reluctantly because the data keep refusing to settle cleanly at -1. But notice what Caldwell and Kamionkowski and Weinberg also admitted, almost in passing, and it cuts the other way. To be sure, they wrote, phantom energy is not something that any theorist would have expected. On the other hand, not too many more theorists anticipated a cosmological constant. That is the trap this whole field is caught in. Both doors lead somewhere no one expected. The comfortable option and the catastrophic option are both, in their way, things the theory did not predict and cannot fully explain. The next piece of evidence concerns the most extreme objects in the universe and how differently the two endings treat them: black holes. In the slow ending, the cosmological constant ending, black holes are the last things standing. They do not last forever. Stephen Hawking showed that they slowly radiate away, evaporating over timescales that defy comprehension. A black hole the mass of the Sun would take something like 10 to the 64 years to evaporate. The supermassive black holes at the centers of galaxies, millions or billions of times the Sun's mass, would take 10 to the 98th or even 10 to the 100th years. A 1 followed by 100 zeros, a Google of years. Numbers like these are not large in any sense a human mind can hold. They are the timescales of patience taken to its absolute limit. In a big rip, black holes do not get that patience. As the phantom density climbs, the calculations grow contested, and this is a place where physicists genuinely disagree, so I will give you both readings. In 2004, Babichev, Dokuchayev, and Eroshenko calculated that a black hole feeding on a phantom background would actually lose mass, shrinking towards zero as the rip approaches, its event horizon dwindling rather than evaporating. Other researchers argued the opposite. The horizon could vanish in a different way, exposing the singularity itself, a naked singularity in violation of one of general relativity's deepest expectations before the final tear. Either way, the verdict is the same in spirit. The most permanent objects in the cosmos, the ones that outlast everything in the slow ending, are unmade early in the violent one. And the Big Rip is not even alone. It is the most extreme member of a whole family of endings that phantom-like energy permits, and physicists have catalogued them with almost clinical care. In 2011, Paul Frampton, Kevin Ludwig, and Robert Scherer described the Little Rip, a universe where the dark energy density still grows without bound and still destroys every bound structure, but does so only in infinite time, with no sudden finite time singularity. A year later, the same group described the pseudo-rip, a gentler cousin still. The cosmologist Mariam Boumadi-Lopez and her collaborators added the little sibling of the Big Rip, where the expansion rate blows up but more smoothly. She has spent years studying what these singularities do to the fabric of spacetime, to wormholes, to the interiors of black holes. Her conclusion is that near these endings, general relativity itself breaks down, and only a deeper theory of quantum gravity could say what truly happens. Even Kevin Ludwig, one of the physicists who mapped this family of doomsdays, allowed himself a moment of plain human reaction in a 2017 review. An energy source that continuously causes an increasing acceleration rate, he wrote, seems unphysical, especially since it can lead to the ripping apart of spacetime itself in this way, which is at least unpalatable in some sense. Unpalatable. That is a physicist in a peer-reviewed journal telling you the mathematics tastes wrong. There are two more traces in this part of the file, and both deepen the strangeness rather than resolve it. The first is a quiet mathematical detail in Caldwell's own work. The time before the end at which any given structure is torn apart depends only on how tightly that structure is bound and on the value of W, and, remarkably, not on the size of the universe or on how much matter it contains. The same equation that unbinds a galaxy cluster unbinds an atom. Only the binding strength and the clock change. That means the destruction is not a local accident of where you happen to live. It is a universal schedule, identical in every corner of a cosmos billions of light years across, written into the parameter itself. What does it mean that the order of the end is fixed by a single number, the same everywhere, indifferent to all the contents of the universe it is dismantling? The second trace is stranger still, and it comes from Mariam Boumardi-Lopez's study of what phantom energy does to the most exotic structures physics permits. In a phantom-dominated universe, her calculations suggest, wormhole throats, should they exist, would not be torn apart like everything else. They would swell. As the rip approached, a wormhole's throat could grow without bound, in some models expanding even faster than the universe around it. A scenario the literature has labeled, half grimly, the Big Trip. And there is one last faint thread that physicists have only begun to pull. Some theoretical work asks whether a big rip would leave a fingerprint in gravitational waves, whether the final tear would imprint itself on the ripples in spacetime that observatories like LIGO now routinely detect. The work is preliminary and contested. No unique signature has been established, and I flag it as exploratory rather than settled. But the image it leaves is hard to shake. The unmaking of everything might, in its final instance, send out a wave. A last transmission from a universe coming apart, propagating outward across a spacetime that is itself dissolving beneath it. So that is the evidence trail. A parameter measured at the edge of the divide. A mechanism that, past that edge, feeds on expansion and dismantles everything on a fixed schedule. A driving field that may be quantum mechanically forbidden. A whole family of related endings. And, beneath all of it, two measurements of the universe that will not agree. Now we test the explanations, because for 30 years, one explanation has been offered above all others, and it deserves a fair and full hearing before anything else. The standard explanation is the simplest one. Dark energy is a cosmological constant. W is exactly -1. There is no phantom, no evolution, no drama. A fixed, unchanging energy woven into space, exactly as Einstein's equations allow. Proponents of this view have a great deal of evidence on their side, and intellectual honesty demands that we state it at full strength. The cosmological constant model fits the cosmic microwave background superbly. When Planck combined its map with supernova data, it measured the present equation of state as -1.03, give or take 0.03, entirely consistent with a clean -1. By most measures, the simplest model still works. Many brilliant people hold this view, and they hold it for good reasons. So let us examine it. We have to ask whether W equals -1 actually accounts for the evidence. It accounts for some of it beautifully. It does not account for three things, and they are not small things. The first is a number so absurd it has its own grim title. If dark energy is the energy of empty space itself, the vacuum energy, then quantum field theory should be able to predict its value. So physicists calculated what the vacuum energy ought to be. The answer they got was larger than the value we actually measure by a factor of 10 to the 120th power. That is a 1 followed by 120 zeros. The prediction and the observation disagree by more orders of magnitude than there are atoms in the observable universe. The physicist Steven Weinberg, who spent years on this problem, acknowledged the gap directly. The measured value, he noted, is some 120 orders of magnitude smaller than the value particle physics predicts. It has been called, without much exaggeration, the worst theoretical prediction in the history of physics. To feel the size of that gap, try to picture it, and then realize you cannot. If you were off by a factor of 10, would call your estimate poor. A factor of 1,000, badly wrong. The number of grains of sand on every beach on Earth is around 10 to the 18th. The number of atoms in the entire observable universe is something like 10 to the 80th. The mismatch between what theory predicts for the energy of empty space and what we actually measure is 10 to the 120th, larger than the count of every atom in existence, squared, and then some. This is not a rounding error. It is the widest gulf between prediction and reality anywhere in science, and it sits at the heart of the very thing that will decide how the universe ends. Now, I owe you a caveat here, because the investigation has to be honest, even when honesty complicates the story. Not everyone agrees that this 120 orders of magnitude figure is a fair prediction at all. The physicist Sabine Hossenfelder has argued that the so-called prediction was never a legitimate one, that the measurable vacuum energy is a constant we infer from observation, and that the dramatic mismatch may rest on a category error rather than a real failure. That objection is on the record, and it belongs in the file. But notice what it does and does not do. It questions whether we should be shocked by the number. It does not supply the number. Whether or not the 10 to the 120th figure is the right way to dramatize it, the plain fact remains. The simplest model takes the value of dark energy as a given. It does not explain why that value is what it is. It writes the number down, it does not account for it. The second thing the simple model does not explain is the Hubble tension itself, the very disagreement we opened with. If W is cleanly -1 and the standard model is complete, the early universe measurement and the late universe measurement should converge. They do not. The gap has hardened past 5 sigma. The simplest model has no room for it. And the third thing is the DESI result. A constant W of -1 predicts that dark energy looks identical at every epoch. DESI, mapping 14 million galaxies, found a preference, modest but persistent, up to 4.2 sigma for a W that changes with time. The simplest model says that preference should not be there. So here is the verdict on the first explanation, delivered not with mockery, but with arithmetic. The cosmological constant is the best-fitting simple model we have, and it may yet turn out to be correct. But as an explanation, it leaves the 3 loudest facts in cosmology unexplained: a value it cannot derive, a tension it cannot accommodate, and an evolution it did not predict. It is less an answer than a placeholder we have agreed to stop questioning. And the moment you stop agreeing to stop questioning it, it stops explaining very much at all. That failure sends most thoughtful people to a second explanation, a far more ambitious one, designed to make the impossible-looking number harmless. The argument runs like this. Suppose ours is not the only universe. Suppose there is an enormous collection of them, a multiverse, each with a different value of the vacuum energy, a different cosmological constant, scattered at random across an unimaginable range. In most of them, the value is catastrophically wrong for life. The energy is so large that the universe is torn apart before a single galaxy can form, or it recollapses instantly. But in a rare few, by sheer accident, the value happens to land in the narrow window that permits stars, planets, chemistry, and observers. And of course, we find ourselves in one of those, because we could not exist anywhere else. The number looks fine-tuned only because we are looking from inside the one place it had to be. String theory, some argue, even supplies the raw material. A vast landscape of possible vacua, 10 to the 500 of them or more, enough to hold almost any value you like. This is a serious argument, advanced by serious physicists, and it must be examined seriously rather than waved away. So examine it. The first thing to notice is that there is no evidence for it. Not weak evidence, none. No other universe has ever been observed, measured, or detected, and by the structure of the idea, none ever can be. A proposal that cannot, even in principle, be tested against any possible observation is not yet science. It is a philosophical position wearing the vocabulary of physics. And there is something worth saying plainly here. For years, defenders of a cause behind the universe were accused of reaching for a maker of the gaps, an intelligent cause invoked wherever knowledge ran out. But what is an infinite, unobservable ensemble of universes conjured into being for the express purpose of explaining away a single inconvenient number, if not a naturalism of the gaps? The same move in the other direction and held to a far gentler standard of evidence. But the deeper problem is the one the physics itself has raised, and it is exquisite. The multiverse argument leans on the string theory landscape, that immense collection of possible stable vacua. Yet in 2018, a group of theorists, including Qumran Vafa of Harvard, working on what they call the Swampland program, proposed something that pulls the rug out from under it. Their conjecture holds that stable configurations of the kind we are talking about, stable de sitter vacua, which is to say a true, eternal cosmological constant, may not exist in a consistent theory of quantum gravity at all. If they are right, the very landscape the multiverse argument needs in order to scatter cosmological constants across countless worlds may be forbidden by the deeper theory. The explanation built to make the number harmless may be standing on ground that the mathematics is quietly removing. And the same conjecture pushes dark energy back toward exactly the place we did not want it. Towards something dynamical, something evolving, something that does not sit safely at -1. What does it mean when the escape hatch built to avoid a conclusion turns out to be barred by the same physics it was trying to escape? There is a third explanation, and it is the quietest of all, because it is less an argument than a promise. It says we do not know why the cosmological constant has the value it has, but science will figure it out eventually. Give it time. The physicist Victor Stenger expressed the spirit of it directly. Any calculation, he wrote, that disagrees with the data by 50 or 120 orders of magnitude is simply wrong. We just have to await the correct calculation. I want to be fair to this, because there is something admirable in it. Science has solved problems that once looked hopeless. Patience has been rewarded before. But look closely at the structure of the claim. It does not present a solution. It presents confidence that a solution exists somewhere ahead, not yet found. We just have to await the correct calculation assumes that the correct calculation is coming and that it will land where the speaker wants it to land. That is not a conclusion drawn from evidence, it is faith in a future discovery. And faith in a future discovery is precisely the thing this worldview tells us not to accept anywhere else. To wave away a present mystery with a promise about the future is to do the very thing science is supposed to forbid. To treat the answer you want as though it were already in hand. Ask a defender of the simple, self-explaining cosmos the direct question. Why does dark energy have the one value out of a near infinity of possibilities that allows a universe with structure and observers in it? Watch what happens. They will redefine the number. They will invoke unseen universes. They will say we will know in time. What they will not do is answer the question on the evidence we actually have. And here, the trail begins to narrow. Step back and look at what survives the testing. Every explanation that tries to make the value of dark energy ordinary has failed to make it ordinary. The simple model writes the number down without deriving it. The multiverse invents unobservable worlds to dilute it and may be forbidden by the deeper physics. The promissory note offers a calculation no one has produced. And underneath all three, the thing they are trying to explain away will not go away. A quantity tuned to a precision of many dozens of orders of magnitude, sitting at the exact value that permits everything we are, balanced on the razor's edge between a slow death and a violent one. What does it mean that every attempt to call this precision an accident requires more faith than the precision itself? That leaves one thing the evidence still demands. Before we can name it, we have to follow both endings all the way to their conclusions and ask what they require and what they leave behind. Begin with the slow ending, the one the simple model favors. The heat death. If W holds at exactly -1, the universe does not tear. It thins, it cools, it empties. Play it forward and watch what happens, one era at a time. Right now, we live in what cosmologists call the stelliferous era, the age of stars, the age of light. It will not last. Star formation is already slowing. The gas that feeds new stars is being used up and scattered. Over the next trillions of years, the galaxies will redden as their brightest, hottest stars die, and only the small, dim, long-lived ones remain. Around 100 trillion years from now, the last star will exhaust its fuel and gutter out. After that, no new star will ever ignite. The lights go out, and they do not come back on. What follows is called the degenerate era. The universe becomes a graveyard of stellar remnants. White dwarfs cooling to black, neutron stars, and the dead cinders of worlds. No warmth, no light except the occasional rare flare. Cold, dark, drifting matter in an ever-emptying void. And then, over spans of time that make the age of the current universe look like a single heartbeat, even that matter begins to disappear. The black holes take over. This is the black hole era. The most massive objects in the cosmos, the supermassive black holes, slowly consume what little remains, and then, over 10 to the 80th, 10 to the 100th years, evaporate through Hawking radiation, bleeding away their mass, one faint particle at a time, until nothing is left but a final, dim glow, and then darkness. When the last black hole evaporates, the universe enters its final state. The dark era. A cold, thin, expanding nothing at very nearly absolute zero, approaching what physicists call maximum entropy. The state of perfect, featureless equilibrium where nothing can ever happen again because there is no longer any difference anywhere that could drive a change. Not destruction, worse than destruction, stillness without end. That is the elegant ending, the mathematically clean one, and it hides a horror that has nothing to do with violence. Here is what an eternal, cold, near-empty universe permits, given enough time, and it has, by definition, infinite time. In a state that hovers forever at a faint non-zero temperature, particles still occasionally fluctuate into existence and wink out. Random, rare, meaningless. But over infinite time, even the rarest fluctuation must eventually occur, and then occur again and again. And the laws of probability deliver a conclusion that the physicists Dyson, Kleban, and Susskind spelled out with full seriousness. Given infinite time, random fluctuations in that void will eventually assemble, by sheer chance, a functioning, conscious brain. Complete with memories, complete with the vivid impression of a body, a life, a world, a past. A brain that flickers into being out of the noise, has a single moment of experience and dissolves. They are called Boltzmann brains. And the mathematics says something that should stop you cold. In an eternal universe, these random flicker brains would eventually outnumber brains like ours, brains produced the slow, ordinary way, by stars and planets and evolution, not by a little, but infinitely. Which means, if this ending is real and the universe lasts forever, the overwhelmingly most probable explanation for any conscious experience, including the one you are having right now, is not a real history. It is a momentary fluctuation in a dying void, hallucinating a world. Now follow that to where it breaks. Picture a reference library that is supposed to contain only true books, but in which, due to a flaw, an infinite number of randomly generated nonsense books are also being printed and shelved. Books full of plausible-looking but fabricated histories. After enough time, if you pull a book at random, it is overwhelmingly likely to be one of the fakes. Now suppose one of those fake books contains the claim there is no flaw in this library, all these books are true. The claim refutes itself, because the very abundance that makes the claim likely to be read is the abundance the claim denies. The Boltzmann brain problem does exactly this to the eternal universe picture. If the theory predicts that most observers are random fluctuations with false memories, then the observations and memories the theory was built on cannot be trusted, including the observations that produced the theory. An ending that undermines the reliability of the very minds that derived it is not a clean ending. It is a logical trap. What does it mean that the most elegant model of cosmic death cannot guarantee that the scientists who built it are real? Now the other door, the violent ending, the big rip. We have already seen its timetable. Now see it. In the slow ending, the sky empties over unimaginable spans. In the big rip, the emptying accelerates toward a single point. And it begins not with fire, but with disappearance. As phantom energy strengthens, the cosmic horizon, the distance beyond which space recedes faster than light, beyond which nothing can ever reach us, does not stay fixed. It closes in. One by one, then in a flood, the distant galaxies cross that shrinking horizon and vanish from view, their light stretched and reddened and finally severed entirely, as if a door were being drawn shut across the universe. The night sky thins. The faraway lights go out, not because they died, but because the space between us and them is opening too fast for their light to cross. Then the horizon comes inside the local group. The neighboring galaxies are pulled away. Then the runaway reaches into the Milky Way itself, 60 million years before the end on Caldwell's clock, and the galaxy's 200 billion stars are scattered like sparks from a struck flint, the great spiral coming unwound. 3 months before the end, the Sun loses its grip on its planets, and the solar system lets go, each world drifting free into a sky now nearly empty of stars. 30 minutes before the end, the Earth, the rock beneath you, held together by its own gravity for 4.5 billion years, comes apart, because the expansion is now happening inside the planet faster than gravity can hold it closed. And in the final fraction of the final second, the expansion reaches inside the atom. The electron is torn from the nucleus. The nucleus is pulled apart into its protons and neutrons, and they into whatever lies beneath. And then the scale factor reaches infinity, and there is no more space in which anything could be near anything else. Not darkness, the end of the stage itself. And here is the detail that turns this from a horror story into a genuine puzzle, the one I promised would matter. A big rip, or any ending that shuts down the eternal cold phase in finite time, solves the Boltzmann brain problem. There is no infinite stretch of flickering void, so there is no infinite population of fluctuation minds, so the trap never springs. The violent ending is, in this one strange sense, the more rational of the two. It does not undermine the minds that study it. Caldwell and his colleagues notice something similar about another deep puzzle, the coincidence problem, the question of why dark energy and matter happen to be comparable in density right now, in our brief epoch. A big rip, they observed, renders the why now question irrelevant. Structure exists only in a narrow window near the onset of acceleration, and then it is gone. we would be living in the only era when there is anything to live in. That coincidence has a name and an author. The physicist Paul Steinhardt pressed the question in the late 1990s, and it has unsettled cosmology ever since. Dark energy and matter dilute at completely different rates as the universe expands. Matter thins fast, dark energy barely at all. So for the two to be roughly equal in density at any given moment is a fleeting condition, like two runners moving at wildly different speeds happening to be exactly side by side for a single stride. For nearly all of cosmic history, one or the other dominates overwhelmingly. They are comparable only for a brief crossing. And we find ourselves alive in precisely that crossing. What does it mean that, of all the eras the cosmos will pass through, we occupy the one fleeting moment when its two great energies are balanced? The same moment, and not by coincidence, in which structure and observers are possible at all. Which brings the case around, at last, to us. Both of these endings share one feature, and it is the feature that should unsettle you most. In both of them, the era of structure, the era of galaxies and stars and planets and atoms arranged into things that can think, is a thin, bright sliver between two darknesses. Caldwell wrote the line himself, almost quietly, in the original paper. Our present epoch, he noted, is unique from the viewpoint that at no other time are non-linear structures possible. Read that slowly. Non-linear structures means everything that is held together. Every galaxy, every body, every brain. There was a time before structure could exist, in the hot chaos after the beginning. There will be a time after, in the freeze or the tear. And we are here, in the lit room between them, in the one stretch of cosmic history in which it is possible to exist at all and ask why. The horizon is already closing, by the way. Not in some distant epoch, now. The acceleration we measure today means that distant galaxies are already slipping permanently beyond our reach, their light already on its way to redshifting into invisibility. There will come a time, in the far future of even the slow ending, when an observer on some world will look up into a sky empty of every galaxy but their own, with no way to know that 100 billion others ever existed, that there was ever a Big Bang, that the universe was ever full. The evidence will have receded past the horizon. They will look out and conclude, reasonably, on the evidence available to them, that their single island of stars is all there is. They will be utterly wrong, and they will have no way to know it. What does it mean that the universe is arranged so that the truth about it is available for only a narrow window, and that we happen to be alive inside that window? This is the part of the case I keep returning to. Not the scale of the endings, the precision of the parameter that selects between them. Here is the second equation that controls our fate, the one DESI was built to measure. To allow for a dark energy that changes over time, cosmologists write W not as a single number, but as a simple line. W of A equals W0 plus WA times the quantity 1 minus A. In speakable terms, the equation of state at any moment equals its present value, W0, plus a second number, WA, multiplied by how much the universe has expanded since then. Two numbers. W0 tells you where dark energy sits today. WA tells you how it is moving. And the entire question of our ending reduces to those two numbers. If W0 is -1 and WA is 0, you have the cosmological constant, the clean, cold heat death. Nudge W0 below -1 and let it stay there, and you have the big rip. The fate of literally everything is encoded in where two numbers fall, and we are currently measuring them right at the boundary where the answer flips. And there is one more relationship worth holding, the one Caldwell's team derived for the timing of the tear. The time remaining until a big rip is, roughly, 2/3, divided by the absolute value of 1 plus W times the present age scale of the universe. Look at what that equation does as W approaches -1 from below. 1 plus W approaches 0. Dividing by something approaching 0 sends the time to the rip toward infinity, which means the closer W sits to that line, the further away the doom. A universe with W at -1.001 and a universe with W at -1.5 are not slightly different futures. They are different categories of ending, separated by the third decimal place of a number we can barely measure. Think about what kind of number this is. Picture a combination lock, but not an ordinary one. This lock has a single dial, and the dial is marked not in dozens of positions, but in a range so vast that the difference between catastrophe and a habitable cosmos lies in digits far past the decimal point. The vacuum energy had to land within a sliver of one specific value, a value tuned, by the measure of the simplest calculation, to something like 1 part in 10 to the 120th for a universe with any structure in it to be possible at all. And the dial was not turned by anyone we can see. It reads, as far back as we can look, as though it came preset. Now, I have to be careful here, more careful than the loud version of this story usually is, because the evidence demands it. I told you the honest complication earlier, and I will not abandon it now. DESI's best fit, taken at face value, does not put W below -1 today. It hints that W dipped below the line in the past and sits just above it now. On its own terms, that points away from an imminent big rip, not toward one. The big rip requires W to fall below -1 and stay there, and that is not what the current best fit shows. An honest investigator states that plainly and does not bury it. But look at what that honest complication actually contains, because it is not the reassurance it first appears to be. For the DESI result to be real, dark energy must have crossed the phantom divide, moved from one side of -1 to the other. And here is the thing the mathematics insists upon. A single, simple field of the kind physicists most readily write down is forbidden from crossing that line. The sign of its kinetic energy is fixed. It cannot flip. To cross the divide, as the data hint, you need something more exotic. Multiple fields, modified gravity, some genuinely new physics nobody has confirmed. So the comfortable reading and the catastrophic reading both lead to the same doorway. Either W sits at exactly -1, a value the simple model cannot explain to a precision of 100+ orders of magnitude, or W moves and crosses a line that ordinary physics says it should not be able to cross. There is no longer a boring option on the table. Every reading of the evidence requires something the standard, unguided picture did not predict and cannot easily produce. So let me tell you where this investigation leaves me. Not as a proof. I am an investigator reading a case file, not a prosecutor delivering a sentence, but as the honest direction the evidence points. When you see a number tuned to 100 orders of magnitude, sitting at the one value that permits observers, balanced on a line that separates two annihilations, you are looking at precision. And precision is the fingerprint of decision. A value that could have been almost anything, and instead is exactly the one thing that allows a universe with minds in it, is not what randomness produces. Randomness produces the other 10 to the 120th possibilities. The dead ones, the torn ones, the frozen before they start ones. We are not in one of those. We are in the single configuration that works, examining the fact that it works, alive in the one window where examination is possible. I have laid out the materialist explanations for that precision, fairly and at full strength, and I have watched each one fail to account for it. The simple model writes the number down and calls the writing an explanation. The multiverse invents an unobservable infinity to drown the number, and may be forbidden by the deeper physics it depends on. The promissory note swears the answer is coming and never arrives. 3 explanations, each built to make the precision look like an accident, and not one of them survives contact with the evidence. What is left, when the explanations that would make it random have all failed, is the possibility those explanations were built to avoid. That the precision is precision because something set it. I do not think this is random. I think the evidence points to a cause. One that is not part of the universe because it set the very constants the universe runs on. One with power beyond the scale of what it made. One with knowledge because the values are not merely large but exact. And one with will because between a near infinity of dead options and the single living one, a selection was made. Power, knowledge, will. Those are not the properties of an equation or a field or an empty vacuum. The laws of physics describe how the universe behaves. They have never once explained why there is a universe for them to describe, or why its dial was set to life. Science answers how. It has never answered why, and on this question it has reached the edge of what how can do. And I will hold to the discipline of the case here because it matters. I am not claiming to see beyond the evidence. I cannot tell you the nature of that cause from a cosmology paper, cannot read its purposes off a graph of W against redshift, cannot pretend a measurement of dark energy hands me certainty about what lies outside the universe. That would be doing exactly what I accuse the others of, treating the answer I want as though it were already in hand. What I can say is narrower and firmer for being narrow. The evidence, followed honestly, points away from accident and toward intention. Where it points after that is a door the data open but do not walk through. That is the read. Now the part of the file that stays open. The honest truth is that we do not yet know the value of W to the precision this question demands. We are standing at the boundary, and our instruments are not yet sharp enough to tell us which side we are on. That is about to change. The Euclid Space Telescope, launched on the 1st of July 2023 aboard a SpaceX Falcon 9 from Cape Canaveral in Florida, is now stationed at a gravitational balance point 1.5 million kilometers from Earth, where it sits in the dark and the cold and watches. Through a 1.2-meter mirror, Euclid is mapping the precise shapes of more than 1 billion galaxies across more than a third of the entire sky, reading how dark energy has stretched and sheared the cosmos over the last 10 billion years. The Vera C. Rubin Observatory, perched on a mountaintop at Cerro Patron in Chile, is beginning a 10-year survey that will image the entire southern sky again and again, catching the supernovae as they flare. Together with the cosmic microwave background, these instruments are forecast to pin down W0 and WA to sub% precision. Sharp enough, at last, to tell whether the dial reads exactly -1 or a fraction below. Sharp enough to confirm or kill the phantom crossing. Within years, not lifetimes, we will likely know which ending the evidence favors. But here is the part that will not close even then. Suppose Euclid and Rubin return the verdict. Suppose they tell us, to many decimal places, that W is exactly -1, or that it is -1.02 and falling. Either answer is a value, and a value is the one thing none of the materialist explanations could account for. The measurement will tell us how the universe ends. It will not tell us why the number was ever set to permit a universe at all. That question does not get answered by a better telescope. It is not that kind of question. It sits on the other side of the line where how ends and why begins, and that line, the data are now suggesting, is not a place science stops by accident. It may be the edge of the map itself. That is as far as the evidence takes us. Let me set the case down where it stands. Two measurements of one universe that will not agree. The Hubble tension, hardened past 5 sigma and still unexplained. A dark energy we cannot see or name, making up 68% of everything. A single parameter, W, the equation of state, balanced on the phantom divide between a cold heat death and a violent big rip, and now, in the DESI data, hinting that it has crossed a line a simple field is forbidden to cross. A cosmological constant tuned to a precision that the worst prediction in the history of physics cannot close. Every explanation built to make that precision ordinary, tested against the evidence and found wanting. Where the evidence left me, I have told you. I do not think a number balanced that finely, selecting so exactly for a universe that can be observed, is an accident. I think precision is the trace of decision, and I think the trail points to a cause with power, knowledge, and will, and then stops at a door it cannot open. That is not certainty about the unseen. It is the direction the evidence runs. If you want to follow the next case the whole way down, the next anomaly, the next file, the next place where the physics runs past the edge of what physics can explain, subscribe, and you will not miss it. And if this kind of case holds your attention, there is a related file waiting on the end screen. Another place where the numbers governing the cosmos turn out to be stranger and more exact than an accident has any right to be. It is worth your time. There is a line the original Big Rip paper chose to end on, borrowed from the poet Robert Frost. Some say the world will end in fire, some say in ice. For most of the last century, we assumed it would be ice. The slow freeze, the clean equilibrium, the quiet. The data are no longer that sure. There may be a third ending the poet never named, the tear. But notice what every one of these endings has in common, and carry it with you when you look up tonight. You are alive in the narrow, lit window between a beginning that could not hold structure and an ending that will not. That window was opened to a precision that nothing in the materialist account can explain. The only question the evidence leaves you is what you think opened it, and whether, standing in the one configuration out of a near infinity that allows you to ask, you are willing to call that nothing. The file stays open.